Hello, everyone. Eric here, and I'm back again to continue our discussion of integration by parts. So, if you recall last time, we said that if I have a integral that looks like this, I can evaluate it by looking at this as a product of two separate functions. So, for example, in this case, I would say that f prime of x is equal to e to the x, and then g of x is equal to x. So we did this specifically so that we could apply a formula. We applied the following formula. I apologize for my handwriting. G of x is, dx is equal to, let's see, f of x, g of x, minus the integral of f of x, g prime of x. dx. Okay, so this was our little formula. So we would look at our integral and say, hey, this is a product of two things. And we'd say, I'm going to assign this one to be f prime. I'm going to assign this one to be g. I will integrate. I will take the antiderivative of f prime, and I will take the derivative of g. And so we said, hey, there is going to be like a proper assignment of f prime and g. Like, oh, if this one's f prime and this one g is g, then we can do the integration by parts pretty easy. But if we make the other choice, then perhaps we will get stuck. So there a lot of times is a proper choice to make between f prime and g, whereas occasionally I would say it's rarer that either way will work, but sometimes either way will work. Now, we did this specifically. We said, hey, let's make it so that g is the thing that will get simple when we take its derivative. It would be really nice if we take its derivative and it turns into some constant value or something close to its constant value. And the thing that we're taking antiderivative of stays relatively simple. So for example, in this case, e to the x doesn't really become this big complex monster of a thing when we integrate it. It just becomes itself, e to the x. So that's very convenient. But let's say we have an example where these things are not true, where me picking either option does not create a simpler end integral for us to evaluate. Excuse me. Messing with Zoom here. Excuse me. All right. Now go away. Go away. All right, cool. Okay. So let's go ahead and do that. Dude, leave me alone. Leave me alone. Okay, so one such integral that I can think of would be e to the x sine of x or cosine of x, either way. And no matter what choice we make for f prime and g, we will have an issue of it will just never get simple. It will never, sine of x will never become a constant value or just x or anything like that. It'll always bounce to the other trig function. And e to the x never becomes anything other than e to the x, whether we take its derivative or antiderivative. So we're kind of stuck in this situation. And I would really like to evaluate this integral to kind of try and show you what to do in this case. This is kind of a special case. And well, we're just going to do it and we'll see what happens. So I'm going to go ahead and assign e to the x to be my f prime. And I'll assign, no, need to do g. I will assign sine of x to be g of x. So that makes g prime cosine of x, and that makes f just e to the x. Oops. Equals e to the x. Okay, cool. So I end up with e to the x sine x minus the integral of e to the x cosine of x dx. Okay, so I now need to evaluate this integral, and I'm going to have to use integration by parts again in order to do so. Go ahead. Okay, whatever. And what's important is that we make sure we make the same choice when we are doing the integration by parts for the following integral. So for example, I said f prime last time was e to the x. I'm going to do that again this time. And then I'm going to say g is cosine of x. It's equal to e to the x. Okay, so f is equal to e to the x. And then g prime of x is equal to negative sine of x. All right. So I'm going to go ahead and rewrite all of this. Sine of x dx is equal to e to the x sine of x minus, and then I'm going to, in parentheses, put all of this other stuff that is my second integration by parts piece. So let's see here. It needs to be f times g, so it is e to the x cosine of x minus, it will be f times g prime, so it'll be e to the x times negative sine of x. So what I'm just going to do is I'm going to put sine of x dx, and then I'm going to make this negative sign a plus sign to account for that second negative in sine of x. So I'm just going to make that positive. Okay. All right. So as I evaluate this, I notice some strange things going on. So I've got e to the x sine of x minus e to the x cosine of x minus the integral of e to the x sine of x, oops, sine of x dx. Okay, so I have a very peculiar thing happening here. So I have part of the evaluation of the integral in question is in fact just the integral itself. So I have some sort of strange identity thing. This is like saying x is equal to 1 minus x, which is a little strange, but this is something that can be evaluated, right? I could do something like say, hey, I could add x to both sides. So I've got 2x equals 1, and therefore x is equal to 1/2. I can do stuff like this. So it's not, I think at first glance, when you first see this, when you're doing integration by parts, it looks very scary. But this is a sign that you are basically done. All the hard stuff is done. All the calculus is done. So once I get to this point where I have the integral is equal to something with that same integral in it, I can treat this as though it's just algebra. So I'm going to do myself a favor, and I'm going to make I'm going to name my integral. I'm going to say let I be equal to e to the x sine of x dx. So this equation now becomes I is equal to e to the x sine of x minus e to the x cosine of x minus I. So I add I to both sides. I end up with 2I is equal to all this stuff. I think you guys see where this is going. Don't worry. I will not drag this on for too much longer. So this would tell me that my integral in question is equal to 1/2 of the stuff on the right-hand side here. So I could say my integral e to the x sine of x is equal to e to the x sine of x minus e to the x cosine of x all over 2, plus a constant, of course, because we are evaluating an integral. So in a way, we never actually evaluated an integral. We did integration by parts a couple of times until we noticed, like, aha, our starting integral ends up in this other side of the equation. And then we used algebra from there to just figure out, okay, well, what is that integral equal to if I just like try to isolate the integral on one side and get everything else on the other side. So this does come up. I would like to point out what our two starting functions were. So remember, this was e to the x and sine of x. So you're not going to get this kind of situation when you have, say, a polynomial or just a power function. Doing integration by parts for polynomials is like kind of long-winded, so we'll just assume it's like x to some power, because x to some power can be evaluated down, whereas this cannot be evaluated down no matter how many derivatives we take. So that is something that you want to be considering as you're going through your integration by parts problems. We now have like these two distinct different varieties of integration by parts problems. One where the stuff inside, the two functions, one of them can be evaluated down as we take derivatives and simplify. We have another situation where we don't have overall simplifications. We have this sort of situation where we end up back at our original integral. And then from there, we do this little trick of where we say like, hey, well, let's give this integral a name and let's just try and isolate it. Now, I will be continuing. I have 2 more videos in mind regarding the integration by parts. And the next one will be the tabular method. So I would highly, highly recommend that you watch the tabular method video to continue on this sort of integration by parts journey. I think that's the most powerful integration by parts tool is the tabular method. So I'll see you in that video. Take care, you guys.